everybody. I am Akshank Tyagi, third year UG at IISc, and so I'll be presenting today on astroparticle physics. By no means I'm an expert on this topic, but I will teach you as much as I know. So please bear with me. First, I would like to start with a small video. It's something that I love and something that actually brought me into astrophysics. So I would like to share that video with you, just to start us off. Okay, there is no sound, but you can still watch it. So you can see it's like a nebulous region. It's a gas cloud, and inside the gas cloud, can you see a star? Star is forming. Gas is collapsing on itself, and it's heating up. Somewhere along the line, fusion starts. And now you basically came inside star's surface. You're seeing the insides of a star. And it's a very violent, hot and high pressure region of the universe. Also, it's not actually observed video, it's just an artist rendition. So don't assume it's a real video. And then at the end of its lifetime, a star goes supernova. One of the most explosive events in the universe. Tremendous amounts of energy, uncomparable to mostly anything else, except for Big Bang, I guess. Big Bang must have had higher energy. Definitely had higher energy. And so you see the gases from inside the star have now been thrown outwards, and it gives rise to these beautiful, amazing planetary nebulae which are colored and symmetric. Quite beautiful when you look at them. And you can see something as a star remnant. It could be a neutron star or it could be a black hole like this. And first, is when a black hole forms, it would not have an accretion disk, but slowly matter would start revolving around it, where it tries to, when the matter falls into due to its gravitational pull, so it starts to accrete, and then it forms an accretion disk around it. This is just an artist rendition that shows the life cycle of a star, and I just wanted to show you, like, it is such amazing things, such beauty that lies in the universe. But at the core of all of this are elementary particles. All the stars that you saw, all the gas, all the star, all of the objects you see in the universe are just particles. So today's discussion will start with a simple question. Can things travel faster than light? So it's not just me teaching you, I need some answers from all of you. What do you think? Can things travel faster than light? Give me answers. Did the students? No? No enthusiasm? Yeah. You are saying that nothing can travel faster than light. Okay, he says nothing with mass can travel faster than light. Not right. Hindu, do you know what? Correct. All of you are physics students. So the first question you should have asked me is, where are you talking about? Nothing can travel faster than light in vacuum, but things can travel faster than light in a medium. So let's first of all, what's the speed of light in vacuum? Yeah, 299792458 meters per second, or simply 3 into 10 raised to the power 8 meters per second. Okay, we'll write this whiteboard. C equals to 3 into 10 raised to the power 8 meters per second. Approximate, very good approximation, everybody can use it. But the problem is, in different media, light travels at different speed. This is the speed in vacuum, cv. But all of you have studied it from class 5th. You studied about refractive index. You know speed of light is slower in mediums. Speed of light is slower in water. Speed of light is slower in gas. Speed of light is slower in gases. Some of the speeds, light in water is 2.26 into 10 raised to the power 8. Light in glass is 2 into 10 raised to the power 8. So, what if there is some high energy particle going through water? For example, electron. Electrons are very small. They can travel at very high speeds, and they can travel in water at speeds higher than speed of a photon or speed of a light particle. Okay? What happens when that happens? It's something special. Anybody knows what this blue radiation is? What this blue glow is? I mean, the answer is written there. It's called Cherenkov radiation. Basically, people observe any kind of highly radioactive substance you have, and you put it in a, let's say, a water container. Then the water starts to glow in this blue light. It gives off this blue light. And this is basically because of the electrons that are coming out of those highly radioactive particles, highly radioactive nuclei. So they are emitting high energy electrons which are moving through water at speeds greater than the speed of light. Okay? No questions? Things can travel faster than speed of light. But one important thing to remember is, how is this blue glow created? It's quite important and it's quite fun to know. So it's something related to the sonic boom. People, do you know what is a sonic boom?
Faster than sound.
Yeah. So if any object, let's say this pen, travels at a speed faster than the speed of sound, something like this cone is created. So a wave is generated whenever sound wave is generated from the tip. So as the tip moves faster than speed of sound, those wave fronts then form a cone. Okay, and that cone has very high pressure, and that can be heard as a supersonic boom. Okay, that same thing happens with light. This is a particle traveling slower than light. So it's producing these light waves, these wave fronts, and they are traveling normally. There is some Doppler shift you can see actually. This side the waves are closer, this side the waves are farther. This is the Doppler shift because the particle is moving this direction. But if the particle is faster than the speed of light, it will create these light cones. The wave fronts are together here. This creates a light cone, and you can actually detect these light cones, and you can tell from which direction the particle is coming. So even though you cannot detect the particle directly, you can detect light coming from that particle. And this is actually what is used in neutrino observatories, Cherenkov radiation. This is a topic I'm not going to take today, neutrino detection, but maybe in a later lecture. Okay, so high energy particles in water can travel faster than light. Anything else? Huh? Okay, very good answer. We'll come to that later. Anything else? Anything else that can travel faster than the speed of light? No answers? Have you heard about this thing? Have you heard about the Hubble expansion?
Yes.
Right? Basically, the universe that we live in is expanding. It is governed by a very simple law. Recessional velocity of a faraway galaxy is directly proportional to the distance to that galaxy. Okay? Velocity of a galaxy is directly proportional to the distance of the galaxy. So it is, how do you actually understand this thing? So this video is quite funny, but it's like a big raisin cake. So these are raisins, and when you bake the cake, these raisins, the cake grows, okay, the cake expands, and the distance between these two raisins will expand also, right? So basically what happened was the raisins moved far away. Try to understand it a little bit. Let's say this is our galaxy. What is our galaxy?
Milky Way.
Correct, Milky Way. We name it MW. And then there is some other faraway galaxy.
M31.
Not M31, not Andromeda, but something even farther. Let's just assume there is some galaxy which is very, very far. This is, let's say, one distance, 1d away. And this is, let's say, half distance away. This is closer right now, this is far away. After, let's say, time t. Okay? This galaxy, let's say, moved to distance 1d. So the space expanded to double its size. The space became double. So how much will this galaxy move? 2d, right? I can't draw it, but just assume. Okay, so this moved 2d distance in the same time, right? So the velocity of this galaxy would be this move 1d. So basically, what is velocity? Delta x over delta t, which is simply 1d over t for this galaxy. And for the other galaxy, it will be half d because it travelled half d in time t, right? So basically, this galaxy was farther away, so its velocity was greater. This galaxy is closer, so its velocity is smaller. Okay? Now one very interesting thing happens because of it that you should know is basically all the galaxies are going farther away. So this and this reason are also going away, right? So this and this galaxy are going away, this and this galaxy are going away. Similarly, these two galaxies are also going away, right? We are here. If there was another galaxy here, this is also going away. Okay? So would you assume that we are at the center of the universe? All the galaxies are going away from us, right? You observe that all the galaxies in the sky are going away from our galaxy, which is the Milky Way. So is Milky Way the center of the universe? Would you assume that? I mean, it's a fairly, means most people would say yes, it is a good assumption, right? We are at the center of the universe. But not so. There is something called the cosmological principle, which states that the universe is homogeneous and isotropic. It basically means it's the same for it's same everywhere. So if you were actually here, then also all the galaxies would be going away from you. Okay? And then you would think this is the center of the universe. So in reality, wherever you are is the center of your own universe, not the center of the whole universe. Okay? So all distant galaxies are going farther away from us because of Hubble expansion. Now, what if the distance is so huge that the velocity of a galaxy is greater than the speed of light? Is that possible? I mean, yes, the universe is so large, if the distance grows, then maybe some galaxy will have speeds greater than speed of light. So that is actually observed, and it's called something called the Hubble sphere. Okay. So this is a very beautiful image which shows the whole observable universe. This is the observable universe for us because we are at the center here, the Virgo supercluster where the Milky Way lies. Now you see this inner ring, this inner blue ring. This is the diameter of the Hubble sphere, basically. So all the galaxies which are currently located here are going away from us at speeds greater than the speed of light. Amazing, right? But and galaxies here are maybe even going twice as fast as speed of light away from us, right? And people said nothing can travel faster than the speed of light. So what is wrong? Is
How
something
do we
wrong
actually
with us?
know that those galaxies are moving faster than the speed of light? We can't observe them.
Very good. So basically what he says is we can't observe them, right? Then how can we tell that these are actually going farther away than speed of light? But that's the whole point. You can't observe them. That directly tells you that they are going faster than the speed of light. Basically, the light from these galaxies will not reach you, and that shows that they are traveling at speeds faster than light. Okay.
We can't observe them. How do we know that they exist?
Basically, you can actually observe them right now. That is the. This is like how much? Yeah, this is like 14 billion light years. This distance. So this is about the distance when they were 14 billion years ago. Those galaxies. Then they were actually quite close by. But now they are so far that they are going at speeds faster than the speed of light. So you can actually see till here. You can see all the galaxies up to here. But all the galaxies which are right now outside the Hubble sphere, their present light will never come to you. So how many of you know that when you actually look out into space, you actually look back in time? Right? When you look at a faraway object, you see its light from when it created in that object and it came to you. So light from any object here will take around 14 billion years to reach you. The universe is not that old. Okay? But at some time long ago, these were closer to us, and then they emitted the light that we can actually observe today. So you can observe all the galaxies still here, but the light produced today in our time, you can never observe beyond this one. Yeah.
So does that mean the universe is slowly disappearing in some way?
Actually, yes. So basically what it means is that this data will stop coming to you at some point of time. But the Hubble sphere is actually expanding. That is something else I'll come back to in a moment. But what it means is that at some point of time in the future, data from all of these galaxies, light from all of these galaxies will stop coming to us. You understand? So basically, all of these galaxies will go beyond the observable universe. That does make sense? Because all of these are going away.
That 1 billion parsec, what's the unit, observable universe?
So parsec is a observable unit itself.
Yeah,
It is around 3.26 light years. Yeah.
Means the observable means universe means how we can define. So this much up to this much area, up to 1 billion parsec, 5 billion parsec. So how we can decide beyond 5 billion parsec? We cannot observe.
So that directly comes from a formula. This simple formula gives you the distance or the radius of the Hubble sphere. It's basically the speed of light c in vacuum divided by h naught, which is the Hubble's constant. The value of Hubble's constant right now is around 72 kilometers per second per megaparsec. Okay? That makes sense. So basically these are the distances. The radius of the Hubble sphere around 4.1 gigaparsec. 1 gigaparsec is basically billion parsecs. Okay, some of you might not know what a parsec is. So it's just a unit of distance. Okay? 1 parsec is simply 3.26 light years. Okay? And 1 light year is distance traveled by light in 1 year.
So what is the difference between visible and observable universe?
Okay, that's a very good question actually. So basically, visible universe, I'll tell you the simple answer. Visible universe is basically till the CMBR boundary, and observable universe is till the Big Bang, beyond the visible boundary. But there is,
So we are
I'm
assuming
not
that
really going into detail. That is the answer.
is the value of Hubble's constant constant over time? It's not evolving.
Okay, very good question, another one. So, people call this the Hubble's constant. It's actually not a constant. It changes with time. Very slowly, but it does change. So, it depends on basically the mass and energy density of the universe. You have it? Ah. In an accelerating universe with a decreasing Hubble constant, the Hubble sphere will actually decrease. So what that means is, well, that's not really good. What I am trying to say is, the Hubble's constant, it's actually part of Hubble parameter h. The current value of Hubble parameter is known as Hubble's constant. Stupid naming, but that's how it is. Hubble parameter changes with time. It's a function of time from the Big Bang.
So
Okay.
further we are looking, the value of the Hubble's constant is different.
Yeah. So basically, when you look at far away galaxies, the measured value of Hubble's constant changes, and it actually increases. So with time, the Hubble's constant is decreasing. That is what we see.
Can we say that with the position the constant is
Sorry?
with the position the constant is different
Yeah.
at 1D, at 2D?
Yeah. So something like that is happening, but the real reason is because you are looking back in time. That's why it is changing. It's not that it is changing with distance, but again I told you that distance is dependent on time.
1D so the light emitted. So
Yeah.
back in time.
So basically, when you are looking far away, you are looking back in time. So you can say that Hubble constant is changing with distance, but that is happening because of the time difference. Okay. Now another thing that can travel faster than light, possibly, is a tachyon. You said that right? Now what is a tachyon? Basically, a particle that can travel faster than light is called a tachyon. The interesting part of a tachyon is that it has imaginary mass. Okay? Not negative mass, imaginary mass. All of you are familiar with imaginary numbers, iota. So, all of you know this formula? The formula for energy of a particle, total energy of a particle, which is moving with velocity v. Okay? This is basically gamma mc squared. M is the rest mass. Now assume that v is greater than c. That is how you are defining a tachyon, right? Whose velocity is greater than the speed of light. So this whole thing becomes more than 1. And this is 1 minus something which is greater than 1. So this thing is negative. So this gives rise to a imaginary portion. Now this energy is something which cannot be imaginary. Energy is something which can be observed, and it must be Vn. Okay? Yeah.
If mass can be imagined, then why not?
Because that is the explanation I said. I did read about it, why it cannot be, but I don't really remember. Okay, it does not come to me yet. So basically, because I'm telling, I read it somewhere, okay? I'm not entirely sure why it was. Energy is said to be only real. Okay? Right? Energy has to be a real quantity, and the denominator is an imaginary quantity. So the numerator also must be imaginary. And that's why we can say the mass of a tachyon, or mass of a particle that travels faster than light, has to be imaginary. Okay? Very simple calculation. One very interesting thing is that you have to, for a normal particle, you have to give it infinite energy to take it to speed of light c. For a tachyon, you have to give it infinite energy to slow it down to c. Basically, it's always moving faster than the speed of light, and when you give it energy, it slows down. For normal particles, when you give it energy, its velocity increases. For a tachyon, when you give it energy, its velocity decreases. Yeah.
Does it mean the galaxies outside that traveling faster than speed of light somehow got infinite energy to
No. Now, yeah, I was supposed to tell you that. The thing about Hubble expansion is, it's not actually breaking the principle of special relativity. It does not. Special relativity says no objects can travel faster than the speed of light in vacuum. But you saw that galaxies are actually moving farther away, right? But they are actually not moving. It's just that the space between them is expanding. Okay? It's just that the two things that were here, they appear to be here. The space between them itself expanded. It's not like the two galaxies moved apart. Okay? There is no motion between them. It appears that there is a relative motion. Why? Because the distance between them has increased. For normal life, we say the distance between them increases, distance between two objects increases because they are moving. But what if the space between them is increasing? They are not moving. They are fixed in their space position. It's just that the distance between, basically, there's a ruler, okay, between these 2 points. It's basically that the ruler got longer. The objects remain at that same position. The ruler itself increased in length somehow. Okay?
Distance are expanding.
So the distance are expanding. The position of the co-moving positions of two galaxies will remain the same, but the distance between them, the actual distance between them will increase because of this Hubble expansion. It's called the Hubble field. Yeah.
So can we see this stretching space as if some medium which allows light to travel faster than the liquid and solid?
Again, come again.
In this medium, like the stretching space, can we treat it as a medium where light itself travels faster than speed c?
No. The light travels at that same speed, c, in that medium also. One interesting thing that happens is, as light moves through this medium, and that medium is expanding, the wavelength of the light also expands with that medium. The velocity remains the same, but it's just that it has to travel more distance. The velocity will remain the same c, because it's black.
Doesn't it depend on how we define distance itself? Like, if we are defining distance as
That is the important thing of SR. Speed of light does not depend on how you define distance. It is irrespective of the frame of reference. So whatever frame of reference it is, if it's co-moving or stop.
let's say if we are observing the same thing outside the universe,
Okay, outside the universe. Okay.
then it appears as if the universe itself is stretching.
Yeah,
Then like the notion of distance changes, doesn't it change?
it does.
But
But the speed of light to you outside the universe, even if you measure it, will still remain the same c. Okay, that's how SR comes out.
Yeah.
Yeah.
I think here another question can be interesting two things. For example, if when we are saying the distance between two galaxies are increasing, I would ask question in another way. Like let's say we are here, and the distance between the atoms in our body or between us two, we are increasing. Does that mean that we are expanding day by day?
Well,
What do you think, sir?
for one thing that was, if you might have observed, was when I was telling you this, I said that the galaxies are actually very far away. Okay. So what that means is that these very far away galaxies do not interact by any other forces. Okay. So these two galaxies are not really gravitationally bound. So they are not the gravitational force that is pulling them inwards is not very strong. Okay, because they are so far away. They are megaparsecs away, which is quite huge. Okay. So then these can expand. The atoms inside our body are bound by electrostatic forces, right? The electrons are revolving around the nucleus. The electrostatic force is quite strong compared to this Hubble flow. So only far away objects which are not very highly interacting, they will experience this Hubble expansion. So let's say if the atoms are there, the Hubble expansion is still expanding the space between those two. But the thing is that the force, the electrostatic force, keeps the atom, brings that electron closer to the nucleus every time the space expands. So the distance between the nucleus and the electron kind of remains the same. But if the Hubble expansion rate increases so much that it maybe overcomes this electrostatic force, then yes, the atoms will split apart.
I think we can just think that the size of the galaxy remains same, only the distance between the galaxies changes.
Yeah, exactly like you said. So inside the galaxy, the distance is not changing as much. Between two galaxies is where you can actually observe the space expanding. You had a question? Yeah.
So my main question is what the sir. So my main question is if it's impacted on the galaxy to galaxy. So we are, and it's all about the space itself. So we are also in our Milky Way galaxy, our solar system is under the Milky Way. So why it's not impacting on the same our universe itself? If everything is expanding, then our in the same each and every individual the galaxy itself, they also have the same impact.
So it's the same thing like an atom.
Yeah,
Just
like that.
instead of electrostatic force, there is gravitational force. So the gravitational force is what is keeping us in that. There is still some amount of Hubble expansion that is there, but it is very less because of one, because the distances between the stars are very less. The distance between sun and planets is very less. So even if space is expanding between them, the gravity pulls the planet closer again. So let's say the planet moved here, the gravity of the sun says, where are you going? Come back here. And it maintains that specific orbit. So that distance is maintained. Same for our sun, for the Milky Way center. The distance remains the same because the gravitational pull is binding them together. Okay? That keeps a fixed distance.
In relativity topic, it was that every universe is expanding. So with that, after some period of time, we cannot observe this universe. It cannot be visible. So right now, it's our nearest galaxy, which is Andromeda. We can observe. So as per means you are telling, so that light which is produced from that universe. So it's so far some billion light years before.
Yeah.
So which for that reason we can observe. So after that we get also disappear.
Yeah. So if I take a galaxy which is right here, okay, there's a chance that it can go beyond the observable universe, and light from that galaxy will actually never be able to reach us. Okay, big time. So basically, there might be a galaxy which is right now visible, but let's say a giga year, 1 billion years later, it might not be visible at all. Okay, there is no way for you to go and observe that galaxy because it has moved outside your observable limit. Light from that galaxy will now not reach ever. Okay, just let's finish with tachyons. So just a quick trivia. There are also two other particles, luxons and bradyons, which is simply light particles and matter particles. So anything which has zero mass is a luxon. So basically a photon is called a luxon, and a bradyon is anything with real mass, non-zero real mass. So all kind of matter particles are bradyons.
So what else is it?
Actually, that's the wrong definition. I'll redefine them. Luxon is something that travels at the speed of light, and baryon is something that travels at speeds less than light. Okay, and that simply gives them their mass. 0 mass, real positive.
So leptons and baryons are part of tachyons?
No. Tachyons is completely different. So these are like dividing all the particles into 3 types. Tachyons move faster than speed of light. Baryons move slower than speed of light. Leptons always move at the speed of light. Examples: photons or even gravitons, maybe, if they exist.
Any number?
Yeah.
Any number means what about what about the speed?
Yeah.
So there that taxon and what also any speed is there. So like 380 or 8 meter per second, so it's light speed.
Yeah.
So what about their speed?
That is what I'm saying. If anything can travel at this speed, that is called a luxon. If it has speed greater than this only, then it is a tachyon. And if it has speeds less than this, then it's a baryon.
Okay, but there is a no the specific speed limit or something. So just
This is the
beyond that,
speed limit.
yeah, this is a light. It's a as a constant speed limit. So beyond that, so it as a considered as a taxon.
Tachyon.
Taxon.
Exactly. Okay, this is all for this discussion. Objects faster than light. We'll move on to our second discussion, which is a simple one. Basically, to give you some idea of scale of astroparticle physics. Now, astroparticle has 2 ends. One is the particle physics, and the other is the astronomical end. And there is quite a huge scaling gap, around 10 raised to the power 40 orders, like 40 orders of magnitude difference. We can, let's say the diameter of a Milky Way galaxy, 10 raised to the power 21 meters. And diameter of atomic nuclei, 10 raised to the power minus 15 meters. In astroparticle, we deal with distances greater than this Milky Way diameter and distances smaller than the atomic nuclei. That is astroparticle physics. Same for mass of the sun, 10 raised to the power 30, mass of the electron, 10 raised to the power minus 31, 60 orders or more, right? So it's a huge conjunction between 2 very, very far away theories, 2 very, very far away phenomena. One that deals with such small particles and one that deals with such huge scale objects and huge scale physics. Also, small fact: mass of the observable universe, 10 raised to the power 53 kgs. Quite huge, unfathomable almost. Might you wonder how did they calculate it? How did they calculate the mass of the whole universe? Yeah.
They use like the existing mass and energy density and the extent of expansion that is
Yeah, very simple. We know the density that we observe in our nearby universe, and then I already told you the distances to the observable universe. That's simple. You have the density and the volume. Find the mass. Okay.
Is it
Simple.
the baryonic mass or
Huh?
is it the only baryonic mass or including dark matter?
Very nice. It's the total mass.
How do you know the density of the
So it again depends on how you measure the mass of the Milky Way, how you measure the mass of other galaxies. Then, basically on that. That comes from certain observables. Like you can observe a microdensity event or something like that. From that you can observe what is the mass of this supercluster, mass of this single galaxy. From that you make estimates. Basically that this much is the mass of a galaxy and this much is the mass of a supercluster which has like thousands of galaxies. Okay? And from that you can actually kind of estimate that this is the average density. It's quite average, okay, like all approximations. Okay. Now we come to particle physics. Okay. Particle physics is basically trying to find the indivisible components of this universe. we found something, we divide it, and we see, okay, this is two components. We divide it further, and we keep finding smaller and smaller particles. We keep finding smaller and smaller portions. Now we come, okay, let's take it from top. This is a normal matter object. Okay, what is it made up of?
Plastic.
Huh?
Plastic.
Plastic.
Plastic, correct. What is that plastic made up of?
Polymer.
Polymers. What is the polymer made up of?
Bunch of molecules.
Molecules. Anybody else? It's simple. Everybody have, you know it. Okay, simple science, childhood science. What is the molecule made up of?
Atoms.
Atoms. What are atoms made up of? Huh? Yes, electrons, protons, neutrons. That is till where we studied in class 12, right? Electrons, protons, neutrons. Now we go one step further. Leave electron, but protons and neutrons that are present inside the nucleus of an atom, they are made up of quarks. Okay? Q-U-A-R-K, quark. This might be a new particle for some people. Some people already know that nucleons are made up of quarks. Okay? So basically, if somebody asks you what is a quark, you say it is an elementary particle that make up nucleon or neutron or proton like particles. Okay? So when you look at the elementary particles, I told you about quarks, right? So I should tell you one more thing. Yes, here you can see this is a proton, right? And proton is made up of two up quarks and one down quark. This is basically the name given to a type of quark. Up quark, down quark. Okay? Similarly, a neutron is made up of two down quarks, one up quark. Okay? Those three particles will give it its mass and its charge. Very simple. So for the quarks, we have up and down quark. We also have an electron. Okay? And then we have something called as a neutrino. All of you have at least heard the term neutrino, right? Okay. So you might have heard it in nuclear decays, right? In nuclear decay, a neutrino is produced in a beta decay, the electron or a positron, right? So basically, we see four fundamental particles: up quark, down quark, electron, and electron neutrino. Okay? But somehow people found more particles similar to these. So we find more quarks. And we found in totality 6 quarks. Okay? And this whole thing is called the standard model of elementary particles. Okay? This is the currently most viable particle physics model. Okay? This which says that there are 6 types of quarks. Up quark and its two flavors, 2 other flavors. So these 3 are called flavors. So up quark, charm quark, top quark. These are 3 flavors of a single family. Then down, strange, bottom, another family. Electron, muon, tau. Okay? This is one family. Electron neutrino, muon neutrino, tau neutrino. Another family. Okay, so these are 3 flavors of neutrinos, 3 flavors of electron-like particles, 3 flavors of up quark-like particles, and 3 flavors of down quark-like particles. Okay? What is same in all of these is charge. Electron has how much charge? What is the charge of electron? Huh? Some whispers, no answers. Okay, it is -1 unit. Okay, even I don't remember. I don't remember what the correct value is. But it is -1 unit. Let's assume -1 fundamental charge. That much you know. -1 of fundamental charge. Now we study protons also have that same charge, -1, +1. Sorry. Protons have a +1 charge, and that is made up of quarks. Up quark and down quark have partial of that. So up quark has a +2/3 charge, and down quark has a -1/3 charge. So basically, proton is 2 upward plus 1 down. Right? Their charges are, up has a +2/3 charge. Okay? And down quark has a -1/3 charge. So you add up these charges, what do you get? +1. Right? 4/3 -1/3, 3/3 +1. So basically this shows that up quark has this charge, down quark has this charge. But you can actually think there can be other possibilities also, right? This could have something else, or maybe their number of up quarks and down quarks was different, or something like that, right? Or what if up quark also had +1/3, down quark also had +1/3, right? So basically this comes from observations. People observe up quark in different states, and then they observe down quark in different other particles, and then they said this must be what their charges from comparison. So basically, if you take proton charge of a proton and then also compare it to neutron, because neutron is also made up of down quarks and up quarks, you can actually find these values, +2/3 and -1/3. Yeah.
So this you told one proton is made by 2 up quark and plus 1 down quark.
Yeah.
So there the combination, total 6 combination, 6 up quark, 6 down quark. So when the 2 up quark has to combine, so which up quark is how it will depend. So each and every matter it will depend the different like up, jump, top, down.
Yes, it does, kind of. So the normal the protons that we observe have only this up quark. Okay, they don't have other quarks. Only that up quark and down quark. Other quarks are not there in a normal proton and a normal neutron. Okay, they're not there.
So who will select? Means how it as a how it will be selected?
I'll tell you. Basically, what the difference is, what the difference between this quark and this quark is mass. They have the same charge, -1/3, -1/3, -1/3. Similarly, up quark +2/3, +2/3, +2/3. What is difference is mass. Top quark is the heaviest quark. It has the mass of 172 protons, almost. Okay, it's heavier than the nuclei of many particles. It's heavier than the carbon atom. Okay, its mass is 172 gigaelectron volts. 172 mass of protons. Okay. So what happens is when a particle is heavy, it tends to be unstable. So it breaks down into simpler, lighter particles. So top quark, it decays into lighter particles which are more stable, which have higher lifetimes. Okay. So how many of you know, like, if something has more energy, it is less stable. If something has lower energy, it is termed to be more stable, right? It's just the same thing. More mass, more energy, less stable. Less mass, less energy, more stable. So that's why these three are the most stable in their families. Okay? Same is also true for electron, but neutrino electron, there is a little difference there. Okay? Here also, for electron, muon, tau is the heaviest, and that's why the least stable. It decays into muon or electrons. Okay? So these particles are called fermions. These particles are called bosons. Anybody knows why? Okay, somebody at the back. Yes. Huh? Correct, but that does not explain why they are called fermions and bosons.
It becomes like integral spin and non-integral spin.
Yes, very good. So basically, these particles have something called as non-integer spin. So spin is like it's like quantum what do you call it? Okay, it's a quantum mechanical property which is similar to angular momentum. All objects, all particles have intrinsically a spin. Okay, it's just a property for you. You have to just say this object, this particle can have this spin. So electron or all the quarks or all of these other fermions can have half or 3/2 or 5/2 spin like this, which is non-integer. For the bosons, you actually see that they can have integer spins. These four gauge bosons have the integer spin of +1 or -1. They can have both spins, +1, -1. Higgs boson has spin 0. Okay, you have a question?
Yeah, in the fermions, the spin is half of integer, not
Yeah.
1/3, 1/3. 1/3, 1/3 doesn't exist, only half of integer exists for fermions.
Basically, yes.
Not integer, it's only
Uh,
half of integer.
Right, no, plus 1/3 and +4 those also exist, but for
5/2 exists. Half
Ah.
of integer exists, but 5/3, 5/4.
those also exist, but for particle combinations. So if you have, let's say, 2 electrons,
So
then they can have something like a
half of,
+4/3.
no, half of it will give us a integer.
No. So basically, this spin is like a vector. Okay. Everybody knows what is a vector, right? This spin has a direction because it's like angular momentum. I already told you, right? So it has a direction also, and it has some magnitude, which you are saying as half. So it can be +half or -half. So you know about vector addition, right? Vector addition is not direct, like summing the two magnitudes. It's not like that. The same thing for spins. When the spins of two particles are added, they don't give you +half equals to 1. Okay? It does not. I cannot really explain you how spins are added. It is even I don't know very well. I did very badly in that. Okay. So these are your fermions. These are your bosons. Why did these names come? Because for non-integer spins, this thing was defined by Fermi-Dirac equation. So fermions. These integer spin particles are defined by Bose-Einstein equations. That's why bosons. Bose is Satyanarayana Bose. Yes. Yeah.
How do you define a particle? Does it have characteristics?
Okay.
Define characteristics.
I wanted to start with that question, but I did not because we are less on time. So, defining what a particle is all about your reference. Okay. Again, everything is related. So this duster, it's quite big for us, right? But assuming we are on a scale larger than the solar system, then you look at this duster, it's very small. Then you can actually consider it as a particle. Okay. If you have a pile of sand, each grain of that sand has a lot of molecules. But that individual particle, individual grain can actually be considered a particle for us. Right? Now we know when we divide that, we get to smaller and smaller particles. So how do you define one particle? It's basically something that looks indivisible to you. Okay? Maybe possibly for something smaller or something which can look into smaller current dimensions, let's say. Quarks will appear as larger units and they are made up of something even smaller. something even more fundamental. So for us, quarks are the particles, right? Like for you, neutrons and protons are the particles. Today I am telling you, no, they are not the fundamental particles. There is something smaller. Okay. So basically, the idea of a smallest particle can change depending on what level you want to look at. Okay. Yeah.
How are we sure that like these particles are not made up of other fundamental particles?
That is what I am saying. We are not sure. Actually, there are many people out there that are sure that they are not the fundamental particles. People out there, have you heard about string theory? Okay. So basically, people say that these are made up of loops or strings, and their vibrations give them their mass and their charge, and basically that's what defines a particle. So basically, in that scenario, the string becomes a more fundamental particle. Okay. So basically, it's just the level that you're looking at. For us, the molecule inside this pen can also be the particle, or if you want to go smaller, at smaller distances, smaller length scales, the atom will be the particle, or maybe the quarks are the particle. It just depends where you are, at what scale are you looking at. Okay, that's how you define the particle. So even this tester can be a particle if you are looking at large scales. If you are looking at scales of kilometers, then this is a particle. Okay. So yeah, as I was coming, these are bosons, these are your fermions. So is that all the standard model has? No. There is something else. They are antiparticles. Okay. How many of you have heard about antimatter? Okay. Everybody reads sci-fi. Antimatter is made up of antiparticles. But what are antiparticles? These are these counterparts of these particles which have the same mass and they have similar spins. Like electron has some specific mass, so it's anti-electron. What is an anti-electron for? A positron. You have heard it? A positron has a +1 charge, but it has the same mass as an electron. So same mass, opposite charge. Okay. So antiparticles and particles have same mass, they have similar spin, but what they have opposite is their charge and their helicity. Okay, I don't really have the time to explain helicity, but it's something. Let's say if you have a ball coming towards you and rotating in one direction, so it has some momentum and some angular momentum, right? So if you take a projection of the angular momentum on the momentum, okay, and if it is if the projection comes in the direction of the momentum, then it has a +1 helicity, and if it is opposite side, so basically the angular momentum is in the opposite side of the linear momentum, then it has -1 helicity. Okay, something like that. So basically, antiparticles have opposite charge and opposite helicity. Also, there is something important called annihilation. Matter, antimatter, annihilation. So whenever a particle and its antiparticle come into vicinity or contact, some form of interaction, a weak interaction between the two, they cause annihilation. Basically, the mass of both of them, particle and the antiparticle, converts into pure energy. This is called matter-antimatter annihilation. This gives rise to pure energy. Okay? So if an electron and a positron combine, they destroy each other. Okay, that's what annihilation means. Destruction. Okay, so that's all for the fundamental particles. And these are some of the values and information in more detail. Basically the mass of each of the particles and the charge. So you can see actually that the quarks are heavier, right, than the electrons, and definitely heavier than the neutrinos, which have on this order mass, 10 raised to the power minus 9. Okay. Also the masses are in giga electron volts, which I already told you is approximately mass of a proton. Mass of a proton is 1 giga electron volt per c square. Okay, approximately. So a quark is very smaller than a proton. Top quark has 173 mass of proton. Electron is very small, but a neutrino is actually much smaller than the other particles in terms of its mass and also in terms of its cross section. Basically, its ability to interact with other particles. Okay, so that's why neutrinos do not interact with other matter particles. Very heavy. They interact like under very rare occasions. Okay, and it's actually very difficult to measure the accurate mass of a neutrino. We only know the mass range. We can put it into smaller and smaller bars. But the mass of a neutrino must be here, in this range. Okay? We don't know the specific mass of the electron neutrino, muon neutrino, or the tau neutrino. So these are the fundamental particles, but these particles can actually combine and make more particles. For example, we already know neutron and proton, right? Made up of quarks. Similarly, quarks can make other particles also. They can make all of these. These are known as baryons. So we have proton, neutron, delta 1, lambda 1, sigma 1, omega 1. It's just this Greek symbol with ON. Okay, quite fun. Similarly, these are mesons. Pion, eta 1, rho 1, k 1. Okay, what is the difference? These are made up of 3 quarks. Okay, or 3 antiquarks. These are made up of 2 quarks, 1 quark and 1 antiquark. Okay, so pion can be made up of 1 up quark and 1 anti-down quark. Okay, now they will not annihilate each other because it's an up quark and an anti-down. Because up and an anti-up they'll annihilate, but up and an anti-down will not annihilate, and they can coexist as a meson. Okay, so these have 2 quarks, these have 3 quarks. Similarly, there are also some very rare states which can have 4 quarks or 5 quarks, tetraquarks. They are called tetraquarks and pentaquarks.
You told me like top quarks are very heavy that they like decay into earth.
Yeah.
Is that the sole reason why like there are no baryons and mesons forming into the top?
Pretty much. Basically, for this particle to be formed, you'll have to have one bottom quark in it, right? So you would want that the bottom quark does not decay. So even if there was some particle which can have a top quark, which does have a top quark, you'll not be able to measure it because the top quark will decay very fast. So basically it means even if there was a particle with top quark, it is harder for us to observe it because the top quark decays very fast. Okay, the decay rate of a top quark is, if I remember correctly, 10 raised to the power minus 8 seconds. No, 10 raised to the power minus 10. So 0.1 nanoseconds, around that. But it's less than that. Basically, it's the upper level. So, one important thing about particle physics is that it also deals with the 4 fundamental forces of nature. You all have at least read about that, right? That all the forces in the universe can inadvertently come from these 4 forces. You have the strong nuclear force, the electromagnetic force, the weak nuclear force, and the gravitational force. Okay? Now these strong force is between nuclear particles, right? And nuclear particles are made up of what thing? What are nucleus made up of? Proton, neutron, which are made up of quarks. So strong force is between quarks. Okay? So inside the proton, the quarks are held up by strong nuclear force. Okay? Then electromagnetic force. The electron goes around the nucleus because of an electrostatic potential. That is your electromagnetic force. And then you have the weak nuclear force, which you might have heard about it a little bit in like decays and like radiation processes, right? Let's say a beta decay or maybe fusion or fission. This is very responsible for. And then gravitation. Everybody has heard about gravitation, right? From Newton's theories to Einstein's general relativity. You all have read about it? Yeah.
How do we model strong forces? Is it like a power law?
Right?
How do we mathematically model the strong forces? Is it a power law?
It's a combination of two power laws. If I remember correctly,
So it's an empirical.
okay, no, that it is a power law, but it can be a combination of different power laws at different distances. So if you might have heard about this, that at smaller distances, electrostatic force is also, it's not directly inverse power. There's also a, like repulsion comes in. Even if you have two electrons, let's say a proton and an electron, they can be overlapping on each other, right? Or like you have, let's take, this is a proton and then there is an electron, okay? So at some distance they will have an electrostatic attraction. But if the electron comes very close to this proton, okay, that is the distance where strong forces might be applicable. So 10 raised to the power minus 14 meters. Along those distances, this electrostatic force might also become repulsive. So basically it's a combination of a power law. It has one which goes b raised to the power 4. I don't remember it, I'll not tell you something else. Okay? So basically something similar comes for a strong nuclear force. It can be written as a sum of power laws.
So it comes from the quantum field theory models.
Yes.
Not empirically.
Sorry?
Not obviously empirically derived.
Yeah, not empirical. There is a theoretical like formula that comes for the strong nuclear force. Now what is important to remember in these forces is the distances on which these are. Okay? So basically gravity can impact on objects at infinite distances. So even if their galaxies are very far away, few megaparsecs, many megaparsecs away, there is still some gravitational force between them. Will be very less, very completely negligible, but still there is some gravitational force. That same thing is true for electromagnetic force. If there is a proton at here and an electron at infinity, it will still have some electrostatic attraction towards this. Okay? Again very negligible, but still possible. So these two are present till infinity. But for strong nuclear forces, the distances have to be smaller than 10 raised to the power minus 14 meters. So this is only possible inside the nucleus. Where particles can come so close that the strong nuclear force starts to activate. More distances than this, the strong nuclear force is almost non-existent. Okay? When particles come closer than this distance, this right here, then they will actually start feeling the strong nuclear force. Okay? For weak nuclear force, will have to come even closer. But one important thing are these bosons. So these are called gauge bosons or the force carriers. Basically, these particles carry the force. These are the basically when you have to transfer information about these forces, they will travel through these particles. So if something which has an electric charge, it accelerates. What does it do? It emits a photon. It emits light, right? Accelerating charged particles emit light. Maxwell's center, right? So, electromagnetic forces, information about electromagnetic forces travel through photons. Information about strong force or the strong interaction is coupled with the gluon. Okay? And for weak nuclear force, you have W plus, W minus, and the Z boson. Okay, it has three particles. W plus and W minus are particle antiparticle. Okay. Similarly, people say that gravitational force can also have a particle. Carrier force carrier. It is called a graviton. So some theories try to explain a graviton, and people are trying to observe a graviton, but they have not been able to do it so far. Yeah.
According to relativity, gravity is because of space-time curvature, and
Yeah.
people are trying to fit it by introducing a new particle. So, will they try to do the same in reverse for like other forces or other forces?
No. For all the things, the force definition came first, and then people got to know, okay, these are particles that carry this force. So people know about electrostatic force beforehand, before photons, right? Slowly they got to know, okay, that light is actually related to electromagnetic force, right? That's what Maxwell did. Maxwell showed that electromagnetic radiation is light. It shows that electromagnetic fields can produce something as a wave which we see as light. Okay? And then people later on, even later than that, they said that light is made up of particle, photon. Okay? It can still be observed as a wave, right? Light particles are both waves and a particle. Same thing is for gravitation. Gravitation is observed as gravitational waves. Okay, GR explains gravity as gravitational waves. So again, if something is wave, it must also be a particle. Okay, so that's why people are assuming. People assume. Okay, then there are other theories also that say gravity must also have a particle. Okay, otherwise why is it special amongst these four? Okay. So basically these are the four wave bosons, photons. Also the electromagnetic force and the weak force, they can actually join together. And they form the electroweak force. So at very very high temperatures, electrostatic force and the weak force can basically act as one. Okay, you will not be able to tell the difference between those. And that is called the electroweak force. So for electromagnetic force, you have the photon, which has this mass, zero mass, right? Everybody knows that photon has a zero rest mass, and then it has some zero electric charge. Then W minus has this mass and -1 charge. W plus has this same mass but a +1 charge. As I told you, these are a particle antiparticle form. And then you have a Z boson, which has this mass and zero charge, and a gluon, which has zero mass and a zero electric charge. Right? Now something interesting is this has zero mass, right? That means it can also travel at speeds of light. It can travel at the speed of light c. But in reality, gluons can actually not travel at any speed. Because I already told you, strong nuclear force exists at very very small distances. So the gluon can only travel those distances, 10 raised to the power -14 meters. That distance is covered at speed of light c. Okay, but it cannot exist outside that nucleus. A gluon cannot exist without two quarks. Okay, a photon can exist outside the system of its production, but a gluon must exist in a system of quarks only. We're trying to understand a little bit. So basically, a gluon can only exist between two quarks. It cannot exist independently of the two quarks, and that's why it cannot travel at this speed. even though it has a zero mass. And then there is something special about this boson called the Higgs boson. This is related to the Higgs field, named after this guy, Peter Higgs. Sadly, he died a few days ago. But he's a Nobel laureate whose main contribution to particle physics was the development of a theory called Higgs field. Okay? Now, you have, I've told you enough times about mass, right? Mass of this particle, mass of that particle, mass of the galaxy, mass of a star, mass of the whole universe. But where does that mass come from? What actually is mass? This guy gave an amazing theory which tried to explain how things get mass. How can you define mass of an object? So if you read about it, Higgs particle has no charge, no color charge, and interacts with mass only. Basically, it does not interact any other way. The Higgs boson only interacts with mass. How? So Peter Higgs said that the whole universe has this Higgs field. He did not say Higgs field. He said there was just some scalar field. Okay? That scalar field is spread uniformly all around the universe. And whenever any object travels through that field, it gets some resistance. Basically similar to a ball going through water. Okay? A ball going through water will have some viscous drag on it, right? Some force on it that is pushing it back. When you move your hand inside a swimming pool, you feel a force, right, that stops you from going forward. He said that is what Higgs field does, but to everything, to all particles. Okay. So a photon which has a zero rest mass can travel at any speed through the Higgs field. Okay, it can travel at the maximum speed possible, which is this. Anything which has a larger mass will get some resistance in that Higgs field, and that's why it cannot travel at this speed. I already told you, right? Any particle which has a positive mass cannot travel at speeds c, right? That is because of this Higgs field, because that Higgs field is resisting that particle from moving at the speed of light c. If something is heavier, it will offer more resistance. For something lighter, it will have less resistance. Okay? So it's an attempt at trying to explain why all particles cannot move at the speed of light c. And what does it mean to have mass?
Higgs boson was just recently detected in 2012.
It was detected in 2012. Yes, so not that recent. But yeah.
It doesn't interact with it doesn't interact through electrostatic forces or any other forces.
No.
How do you measure such a particle which just interacts gravitationally on through mass?
So a little bit history. Higgs field was actually proposed in 1966. So people were trying to find the Higgs particle or the Higgs field or some other form of like observable for the Higgs field for almost 50 years. And in 2012, they finally observed the particle which they thought could be Higgs particle. Okay? It was so well sought after that some people even called it the God particle. Okay? So how do they actually measure such a thing? Now we know that what happens in a hadron collider. Where was it observed? The Large Hadron Collider at CERN. Okay? We know what a Large Hadron Collider is. What the Large Hadron Collider is. Basically, remember these particles? These are called hadrons. Right? Baryons and mesons are called hadrons. So anything made up of quarks is called a hadron. So what does the LHC do? It takes hadrons and collides them at very, very high speeds. Speeds close to the speed of light. it is almost 99.9999% the speed of light. At those speeds, it takes a stream of protons and collides them. And when those very fast moving protons collide, they actually generate, because they have very high energies, right? Because they are moving at such great speeds. So basically they convert that speed energy, that kinetic energy, into mass. That mass, that energy, collisional energy, can give rise to massive particles. So basically, I told you about annihilation. Matter, antimatter can interact and give energy. The opposite is also. Energy can give matter and antimatter particles. Okay? So when this very high energy, collisional energy, is generated in these hadron colliders, it creates this particle. It creates the particle. If I remember correctly, the mass of a Higgs particle is supposed to be 17 gigaelectronvolts. Or 16 or 17.
So you just look at the mass defect of.
So you basically look at, no, you don't look at the mass defect. You basically know what will the Higgs boson decay into. Because it is also very massive, right? So it will further decay into smaller particles. So you cannot observe the Higgs boson directly. You cannot observe a mass defect. You only observe basically the further particles that are formed from that decay of that Higgs boson. So from those particles that are produced, you can backtrack. You see only the electrons or the muons, but you can backtrack and you can say they must have come from a particle which was this massive. And that mass matched quite close to the Higgs, the proposed Higgs mass. And so people said that, okay, the observed particle was the Higgs particle. Yeah.
So any particle could have some mass which should like interact with the Higgs field.
Yeah.
And Higgs field like Higgs boson is something that Higgs field like photon is to electromagnetic field.
No. Basically, Higgs boson is not a force field. Some people actually suggest to think of it as that the Higgs boson itself creates the Higgs field. So people suggest like during Big Bang, after Big Bang, sorry, a lot of Higgs particles were created and they basically took their positions in space. And when they condensed, they formed the Higgs field. So basically, they formed like a lattice, okay, like cubical lattice, where each vertex is a Higgs boson, and they form the Higgs field.
So for the Higgs boson to have mass, it should also react with its own field.
Exactly. So that is what happens. So the Higgs boson can interact with other Higgs bosons.
So if you take only one Higgs boson, it doesn't have any mass.
Without the Higgs field, nothing will have mass. Basically, you cannot measure that mass. Even if something has a mass, if there is no Higgs field, you cannot measure that it has a mass.
We are having only one Higgs boson.
Okay.
So it is having its own Higgs field, but there is no other Higgs boson. So can
Yeah.
it react with its own Higgs field?
It will not interact with its own. So that is what I am trying to say. Like a single particle having a field is not very well defined. People just say that, okay, a lot of these particles coalesced into a field, into their specific positions that form this Higgs field. Okay? That gives you some sort of.
So also does this have something to do with gravity, because gravity is associated with mass? So or something.
No. So, like, these two do not match at all. Even though this gives them the mass, and then mass shows how gravity works. Mass actually, gravity depends on the mass, and this tells how that mass is coming. Okay? So, I was actually supposed to teach dark matter and dark energy also, but I think it's pretty late and we should wrap up with this. I'll continue with this in the next possible lecture, whenever that happens. Okay, so that's all for today. If you have any other questions, I would like to have. Thank you. Also, thank you the Astro coordinators for inviting me for this talk, and thank you everybody for being such patient listeners and for interacting.